Welcome to this lesson on CHATELIER'S principles, the question of the day. What do you do when you're cold? What do you do when you're hot? And what do you do when your hands are dirty? And why do you do all these things? You may have learned in biology a term homeostasis. That's kind of what equilibrium is in chemistry. When you're cold, you are going to shiver, and when you're hot, you'll sweat. When your hands are dirty, you wash them. And the reason is to get back to normal, to get back to comfortable. And we today are going to look at how equilibrium reactions do the exact same thing. They work to get back to normal. And this was put together by some, I'm assuming, French guy, Le Chatelier, and he looked into how equilibrium reactions got back to comfort and got back to normal, returned to equilibrium under certain stresses. There are three primary ways to disturb equilibrium, and the result of this is going to be the reaction working to get back to equilibrium. So the first is to change the concentration. Remember, equilibrium, the concentrations have to be constant. Well, if we mess up the concentration, then they're not constant anymore. They're not in equilibrium. So adding some stuff or taking away some stuff, either the reactants or the products, is how we can change concentration. Next, if we are working in a gas system, we can change the pressure, which kind of changes the concentration a little bit, because we can change the pressure either by adding a gas and filling up some space and increasing pressure, or by squeezing the reaction and reducing the volume. Either way, our particles are either going to be squished together, increase in concentration, or they are going to be spread out, which would be the equivalent of a decrease in concentration. So any which way, changing pressure on a gas system is going to disturb equilibrium. Last up, we can change the temperature. We can either make it warmer or colder, and this will affect reactions based on the delta H of their reaction. So whether it's an endothermic reaction or an exothermic reaction, the change in temperature will affect them a bit differently. So the way that I have always looked at Le Chatelier's principles is under the little trick: add, away, take, toward. So the reaction is always going to shift to get itself back into equilibrium using this kind of add, away, take, toward trick. Let me show you. We're going to keep it really simple and look at just the Haber process, which is the synthesis of ammonia from its elements. We discussed in the video on equilibrium that this is an equilibrium reaction, and we know this because of the double-sided arrow. It means that some of the reactants are going to become products at the same time that the products become reactants. So we're kind of in this never-ending loop. This reaction has a negative delta H at 91.8 kilojoules. Now, let's see what happens if we manipulate the concentration here. Let's say we add a bunch of nitrogen to this reaction. Well, now our concentrations are all out of whack. To get this reaction back to normal, the nitrogen and the hydrogen are going to work overtime to make a bunch of ammonia, because they want to get this reaction back into equilibrium. So this is where add, away, take, toward comes in. If you add a bunch of nitrogen, the reaction is going to shift away from that nitrogen. Try to get rid of it, try to use it up. So that is why we still have this double-sided arrow, but I've added an extra arrow pointing to the right, kind of indicating that we are going to shift this reaction to the right to get that nitrogen used up, turn it into ammonia, and then get back into our cycle. Now, on the flip side, if we were to remove a bunch of nitrogen, now we have an excess of ammonia compared to the reactants here. So if we take out the nitrogen, then the reaction is going to shift toward the nitrogen. And that's indicated here with a left shift. We would say that it shifts left. We have an extra arrow pointing to the left. The ammonia is going to work overtime to break apart and replace that nitrogen that we have since removed. This is true whether I'm looking at the nitrogen, the hydrogen, or the ammonia. If you add something to the reaction is going to shift away from that thing, add, away. And if you take it out, then the reaction is going to shift toward that thing that you've taken out in order to replace it. Pressure is a little bit interesting. If the pressure changes, then the equilibrium is going to shift to get back to normal. So whichever side has more moles of gas is going to have a larger volume overall and is going to exert more pressure on the overall reaction. So if we look again at this Haber process, we have 4 moles of gas on the reactant side. We have 1 nitrogen and 3 hydrogens, compared to over here, we have only 2 moles of ammonia. So let's say we added a noble gas. Noble gas is not going to really participate in this reaction. It's just in there to take up space and thus is going to increase the pressure. We can also decrease the volume. We can take the reaction vessel and literally squish it, and that's the same effect as increasing the pressure. So let's say we do either of those things. Maybe we do both of them because we're feeling kind of crazy. This reaction is going to shift to whichever side is going to have the fewest number of moles in order to kind of relieve that pressure. So increasing the pressure or increasing the volume is going to force the reaction to shift to whichever side has fewer moles of gas in order to relieve that pressure. In our case, we are going to shift to the right because the ammonia is only 2 moles, where the hydrogen and the nitrogen are 4 moles together. The converse is also true. If we were to increase the volume, stretch out this reaction vessel, we give our particles a lot more space. They're kind of like, oh, where did everybody go? The pressure's lost. So what happens is the reaction will now shift to whichever side has more moles. So in this case, it's going to shift left. You can still kind of use add away, take toward here. If you add pressure, then we are going to shift away from the side that has a lot of pressure. So looking back, adding pressure here, we are going to shift away from the side of the reaction that has more pressure. And if we take pressure out, we reduce the pressure, then we are going to shift to the side that has more pressure. So if we take it away, we're going to shift toward the side that has more pressure. So you can look at it that way as well. And now we have this kind of strange thing. If the reaction has the same number of moles of gas on both sides, so let's say it's 2 moles on one side and 2 moles on the other, then changing the pressure will have no effect. Everything is just like a little bit more uncomfortable, but the reaction is not going to shift left or right because we have the same number of moles on each side. No shift is going to get us back to equilibrium. Now, in terms of heat energy, like I said earlier, that delta H is really going to play an important role here. So increasing the temperature is going to favor the endothermic reaction. Remember, endothermic reactions are trying to absorb energy. So if we add a bunch of heat, the endothermic reaction is like, oh, hey, there's a lot of heat here. This is fantastic. I've been looking for all of this heat. So increasing the temperature is going to favor the endothermic reaction. In this case, we have, as it's written, an exothermic reaction, meaning that the forward reaction is trying to get rid of heat. It's trying to release it, right? That's what this negative delta H is for. If we take away the heat, then the ammonia is saying, okay, cool, let's break apart. Let's go backwards. Remember from the Hess's law video that if you flip a reaction, you flip the sign of the delta H. So this reaction of nitrogen plus hydrogen gives ammonia is negative, but ammonia breaking apart into hydrogen and nitrogen is a positive delta H. You flip it. So the reverse reaction here is the endothermic reaction and loves the addition of heat. It's trying to absorb a bunch of heat. The exothermic reaction, on the other hand, is trying to get rid of heat. So if you reduce the temperature, maybe you put this in an ice bath, you put it in a fridge, something like that, the reaction has a better time offloading its heat because the surroundings are cold. So reducing the temperature, the exothermic reaction is like, oh, good, we're trying to get rid of this heat, get rid of it. And every time you reduce the temperature, the exothermic reaction is going to be happy. So in this case, the exothermic reaction is the forward reaction. If you reduce the temperature, the exothermic reaction is going to work a little bit overtime, and we are going to wind up shifting to the right. Now, Le Chatelier's principles are really difficult. It's not something that you learn just from me teaching it to you. You're going to have to get some practice. So make sure that you practice. Take a look at all of these reactions again and really take your time to learn and understand the principles. If you have any questions, please leave them in the comment section below the video. Subscribe so you don't miss the next lesson. I will see you there. Bye.